Okay, guys, now comes to the step that we're going to apply these theoretic results to more practical control system analysis. And I wanted to address essentially three things. First, I want to go through this example today to talk about how passivity, pop-off inequality, plays from an energy perspective in this realistic example. Second, I want to transform our parameter adaptation algorithm into this block, our theta hat adaptation law into this block, and utilize the passivity concepts, strictly positive real conditions to analyze hyperstability of the system. And along the way, let's think about this question. If we have a hyperstable system, can we imply stability? And if it's the converse also true, if we have a stable system, can we say it is hyperstable? Think about these two as we work on this problem. Let's start with this example first. We have a mass with force applied, and then we have a velocity as the output. So from Newton's law, we know that the governing equation is mx double dot, x is the position, bx dot plus kx equal to u. So therefore, let's write out the transfer function from the force to the position, which is going to be essentially 1 over ms squared plus bs plus k. After you apply Laplace transform to these. Right? So division, the ratio between x and u is 1 over ms squared plus bs plus k. This is the position as the output. For this problem, the velocity as the output is the derivative, right? So the v is the Laplace transform because v is x dot. So vs is sxs. So therefore, the transfer function from u to v is going to be sxs over us. The top part is v, and then the bottom part is u. So therefore, the transfer function is going to be this. Now, let's consider a really general result. We have this physical system, and I can make my control in a lot of ways. Now, the powerful thing about hyperstability is that we will be able to make conclusions about if this is our controller, if this is our plant, we are going to tell something about this plant under a very, very general nonlinear controller. The notations are going to be W, U, and V. So our setup is I have this mass, moving mass. I'm going to apply some control algorithm to it. And what we're going to talk about is take a lot of controls that can be framed as a nonlinear block over here. We will be able to show that the system is going to be guaranteed to be stable as long as the nonlinear control is passive. So that's actually very generic and powerful conclusions, right? So let's do that. We'll show passive nonlinear control block. These two guaranteed hyperstability as long as it's passive. So let's put this into mathematical term first. Passivity will imply we satisfy this Popov inequality. W, the output block is W, the input is V, and they are scalar, right? These are all scalar signals, so I don't need to put transpose. I can just say W V is going to be lower bounded by some negative gamma square. And from an energy perspective, here is what we have. The moving mass has two energy, the system has two energy components, kinematic energy and potential energy. So the kinematic energy is going to be half of m times v. Kinetic energy is half of mv squared, and potential energy is half of kx squared. We're assuming the initial velocity is v naught, initial position is x naught. So from an energy perspective, the energy at T1 minus the energy at initial time should be equal to the energy that is supplied to the moving mass system. All right? So the physical meanings are, again, this is force. Force times velocity is the energy supplied to the system. So essentially is this term. And we know this term is going to be is this term. It's the input u times the v, then to the integration. Right? This is the force, not w. W, there's a subtle difference between u and w because we are putting a negative sign. We are doing a negative feedback control law. Okay? So this is negative W V dt. So from here, we can see that put a negative sign out, then we can see this term, this whole thing is going to be bounded from the top by gamma square. Right? So minus multiply negative on both sides. You need to change the positive larger than or equal to less than or equal to. And this makes physical sense because it is basically saying my energy at T1 should be at most the energy at the beginning plus the energy that's supplied to the system. You cannot exceed certain value because it's a physical system. Now, for this moving mass system, we all know how we usually define the states, right? So define the states. The usual way we define states are we choose velocity and position as the states. So for this problem, let's normalize things a little bit to make it more apparent. So let's normalize our position a little bit to be x let's do half of k over 2 x position. So let's say xs is the state vector. It is a normalized version of the position and the normalized version of the velocity. And in this way, we can see immediately this term is nothing but the 2 norm of the state vector. So the 2 norm of the state vector is going to be k over 2 x squared plus m over 2 v squared. Some normalization will make us be able to represent this energy term as the norm of the state vector, just for convenience of representation. All right? So therefore, what we have is the state vector at time t1 minus the initial norm is going to be upper bounded by some positive terms. And we can write it slightly more compactly as using the norm notations. The 2 norm of the state vector at a given time t1 will be guaranteed to be lower bounded by something that depends on the initial condition plus some positive terms. This is for any t1. And this is actually a very strong condition now becoming, right? This is saying regardless of how you apply your control law, we can always guarantee the state will be bounded at any finite time. So if you recall our stability definitions, right, this is essentially something in the sense of Lyapunov, stable in the sense of Lyapunov. And in our context, we use hyperstability as to define. This is the definition of hyperstability. So the state always bounded, right? And actually the energy is also always bounded, regardless of T1 and the explicit control law. All we need is the control satisfies the Popov inequality and is a passive nonlinear block. All right, so this is put it here. You can recall the definition of hyperstability is that the state will be bounded by something that looks like this that depends on the initial time. So that is the mathematical analysis. And the principle or the concept is now perhaps will suggest itself. You can see how things play, right? we're saying the nonlinear block will be at least lower bounded by negative gamma square. Okay? And the negative sign will cancel with this negative sign over here. And the in term make the physical connection to here, suggesting that the energy that is supplied to this LTI block will be bounded. And because this LTI block will be, if you think about this is a passive system itself, it doesn't generate energy. Then if you supply finite energy to a system that doesn't generate energy itself, then the output will be bounded. It's going to become a hyperstable system. And if this block consumes energy itself, if this is strictly passive, then if you supply finite energy to it, all the finite energy will eventually be consumed. And the only way for for the output to exist is to gradually reduce to zero. The energy has to die down in the end. And then, more specifically, the energy in terms of this, if you think about this is zero, the only way is for both the position and velocity to be zero. So all the states will converge to zero. So that's the physical intuition about Popov inequality, passivity, and the stability. So that is for this picture. Now, let's come back to here, because now we're talking about hyperstability, and you see how energy perspective will play a role in here. Let's think about these two questions. If a system is hyperstable, can we say it is stable? Which is true, right? We already talked about what it means here. So this is true. Is the reverse true? If I have a stable system, can we guarantee hyperstability? All right? So this puts us into a perspective how strong, whether hyperstability is a strong requirement or not. Okay? So as an example, let's think about if we have a system that looks like this. This is a simplified example, but this, we already said, if it's a static gain that is positive, then this satisfies, this is passive. Okay? It satisfies the Popov inequality. And the whole feedback system, overall transfer function, is 1 over s minus 1, 1 plus k times 1 over s minus 1 from block diagram analysis. And it's going to be 1 over s plus k minus 1. And because k is positive, k is larger than 1, k minus 1 is positive. So its pole is at negative k minus 1, is going to be on the left half plane. So the closed loop is stable, right? So this is checked. But it's not really hyperstable because this linear block over here, its pole is at s equal to 1, which is on the right half plane. So this is not stable. This is not positive real or strictly positive real. All right? So this is not hyperstable. Okay? So hyperstability is a stronger condition than stability. And the reason for that is because we are handling adaptive controls. We are handling the scenario where the control law is actually non-linear. Okay? Adaptive control is not a linear time invariant control algorithm. So that's the two questions here. All right, so now if we have a parameter adaptation algorithm that looks like this, let's think about how to put this into this block so that we can analyze stability. There are two steps, and one of the steps was actually mentioned a few lectures earlier. The first step is, this is still a lot of terms. This is the a priori adaptation law. So the first step is to recall the a posteriori adaptation law, which was this. We spent some time to derive the relationship between the a priori adaptation error and the a posteriori adaptation error. So we can simplify the terms a little bit. And the second step is, someone said, why were we caring about the state going to zero in the hyperstability definition? We said asymptotic hyperstability means the state of this LTI block will go to zero. And someone was commenting, can we have an equilibrium that is not at zero, right? So this is related to that concept. So the way is some normalization. We're going to define the parameter adaptation error, the difference between the true parameter and the estimated parameter as theta tilde. We're going to define it by saying that theta hat minus theta is theta tilde. Okay? So this is the parameter estimation error. So I use a triangle equal sign to indicate this is defined this way. Pay a little attention about the terminology. So this epsilon, this is the adaptation error. Right? This is what's going to drive this adaptation law. And this is the parameter estimation error. This is the error between the true and the estimated parameter. That's the definition. All right? So this way, you can imagine what we are trying to achieve. we're going to show that theta, eventually some concept similar to, we're going to try to show that theta tilde will be going to 0. All right? Not precisely, but in this direction. And the way that we're going to approach is to look at the arrow term. Okay? So with this concept of theta tilde, we can see that the a posteriori estimation error, adaptation error, is going to be the true output minus theta hat k plus 1 times phi k. All right? The true value is theta hat transpose phi k minus the true y is theta transpose yk, not a hat. And then the estimated is this. Or using our theta tilde notation, this is going to be negative theta tilde transpose times phi. All right? So our goal now from the remaining analysis, our goal for this lecture is to show this adaptation error will go to 0. All right? For today, we will make the assumption for today, we will show the case where we have a constant adaptation gain. Next time, we're going to work on the time-varying adaptation gain. Now we have the arrow term, and then we talked about how we normalize this adaptation equation by introducing the theta tilde sign. So with all these, we will have theta tilde. So basically, it's to change all the hat into some term related to theta tilde. So theta tilde is theta hat minus theta, and it equals theta hat k minus theta plus f phi epsilon k plus 1. This is plugging in the adaptation algorithm of theta hat. So this is tilde k, theta tilde k. And we are using a constant adaptation gain again. So this is f without the k index. We're going to now draw this linear and nonlinear block diagram. All right? So the way that we're going to do is as follows. We want to make this to be 0. All right? So the hyperstability theory is going to be able to give that to us if we put epsilon k plus 1 here. And then epsilon k plus 1 drives the adaptation in this way. So epsilon k plus 1, if we multiply this with phi k, this is multiply. And then multiply with this adaptation gain f. Then we have this term. All right? This is f phi epsilon k plus 1. It will be able to give us theta tilde k plus 1. I'm trying to massage this equation into the bottom over here. This add with this term added with theta tilde k will give us theta tilde k plus 1. And then theta tilde k plus 1, theta tilde k, these are just the same thing at different times. Using our delay operator, theta tilde k is nothing but theta tilde k plus 1 operated to a one-step delay here. All right? So now we have this equation. Now everything is combined into the block diagram here. The only thing we need to take a look finally is how epsilon k plus 1 depends on theta tilde k plus 1, which is also on the whiteboard here, right? Theta epsilon k plus 1, it is negative theta tilde k plus 1 transpose times phi k, right? So we have already theta tilde k. We multiply this with phi k. Then we will get epsilon okay, so this is negative phi transpose k times theta tilde k plus 1. This is positive. So the signal here is phi transpose k times theta tilde k plus 1. And we add another negative sign here. This becomes this, right? So this is negative theta tilde transpose. I swapped the transpose sign again using the trick we talked about for vector multiplications. So now we have, this is exactly what's on the right and this is what's on the left. So we can see that the LTI block is extremely easy. It's just 1. So everything now is combined into the picture here. Now, this is SPR, right? Obviously, constant is stable, and we had an example. This is strictly positive real. We just need to show that the bottom side is passive and satisfies the Popov inequality. So let's talk about Popov inequality. And let's again remind ourselves what are the input to and the output to this block. To show Popov inequality, we need to consider the input and the output to this whole block. All right? So need to show this is a discrete time system, so we need to use the discrete time Popov inequality. Output, okay, is going to be lower bounded by some negative number. Let's take a look at that. So, the basic principle to show this is actually something we already mentioned. Theta tilde k plus 1 shows here, and we have an epsilon k plus 1 here. We know from this equation, epsilon k plus 1 actually relates to theta tilde k plus 1 and theta tilde k. All right? And then if we do the product between these, we have a theta tilde k plus 1 term. And this relates to theta tilde k plus 1. So there is some quadratic term about theta tilde k plus 1 here. And quadratic terms are always non-negative. So that will give us some bounds very soon. That's the key concept. And the details are as follows. So we know theta tilde k plus 1 equal to theta tilde, I'm going to put it into this way. All right? So we have phi and epsilon. We have phi and epsilon. So this is K0 to K1. We can switch the order and then have this. So now phi and epsilon are in this order, appearing in this order. So therefore, this is theta tilde transpose k plus 1. I have an f here that is a little bit annoying. So what I'm going to do is I'm going to do f inverse f phi k epsilon k plus 1. And this thing is now theta tilde k plus 1 minus theta tilde k. And the quadratic terms are appearing from here. So plug this inside, we are going to get a quadratic function about theta tilde k plus 1 minus something that is cross product between theta tilde k plus 1 and theta tilde k. Now from here, how can we move forward? We now know this is probably going to give us a lower bound already, right? How do we handle this thing? It's not obvious. This will be lower bounded by something. Okay. This is another general trick or general rule of thumb. When you see cross product between two vectors, you can think about something related to creating a square term. Because if you see, if it's scalar case, if you see A times B, then you can put it into something like this. Let's say negative A plus B, negative A times B. Negative A times B will appear when you have A minus B square. All right? And this is a square term, and will be lower bounded. So the only difference is this is vector case. So let's do that. We're going to do complete the square. And I'm going to introduce the first thing doesn't change. I'm going to add and subtract something related to theta tilde k. So I added and subtracted a quadratic function about theta tilde k, because in this way I can create this square term. So I can see that if I have half of theta tilde k plus 1 minus theta tilde k square, I'm going to use this is the vector case. So I'm going to do this. This is a square term. This is always positive. I know this guy will give us half of theta tilde transpose theta tilde k plus 1, and then minus this F inverse term. Okay? F inverse. So this is going to give us, this is the first product. The second product is going to be F inverse theta tilde k. And then this times this is going to be negative theta tilde k, F inverse theta tilde k plus 1. Then last two is going to be this. And you see here, this is going to give us this cross product term, right? This term, they are all cross product. And they are equal to each other, right? They are just the transpose of each other. Okay? Take the transpose of this one, it's going to become this. So they are the same thing. They're both scalars. So we have the cross product term here, which is going to be here. And I intentionally added a half because you can see this add with this is going to become 2 times this cross product term. And divided by 2 is going to become this. Just some normalization effect over here. So this is going to give us, now let's look at this a little bit carefully. We need to create this. You see what we need. We need half of not this term. We need half of the first big term over here. All right? And then we need entirely this negative cross product term. All right? So we can write it as, after this add and subtract, we can write it now in this way. So I break it the first term into two. Now I have this first term. And then I already have this cross product term. Now I need half of the quadratic term about theta tilde k. So I'm using half of this here. I'm using the positive of the half here. And the only thing that I haven't used is the negative component. So this is going to become minus half. So that's the whole picture. This is exactly this version. And then inside, this is a quadratic function that is always positive. All right? Take a picture of this whole thing. We're going to come back to this next time.